Okay, hello everybody. Welcome to today's installment of the California Dreams Technical Seminar Series. I'm excited today to have with us Hamidreza Agazi from University of California, Irvine. He has been at California, Irvine since I think 2019. I'm not sure that I have that exactly right. He's a senior member of the IEEE, doing work in RF, millimeter wave, and terahertz circuit design for imaging, sensing, and communication applications, all right within the sweet spot of what we're doing in California Dreams. He is widely published among the most prestigious journals in the area and has received awards such as the Cornell Graduate Fellowship, Jacobs Fellowship, ECE Innovation Award at Cornell, Cornell Scale Up and Prototyping Award, Best Invited Paper Award at 2019 IEEE CICC, NeurIPS ML4PS Reproducibility Award in 2024, and lastly, the NSF Career Award in 2025. So congratulations on that recent and prestigious award. Please take it away.
Thank you very much to Steve and Amy for the introduction and organizing this event. Good afternoon, everyone. I'm very excited to have the chance of sharing our results and research in the last 5.5 years at UC Irvine with you. So the talk is going to be about multi-band millimeter wave radar systems implemented in CMOS technology. The outline of the presentation will follow an introduction and motivation, followed by some technical description of what radar solutions are needed. And then I will show two chip solutions, one for multi-band coherent radars to achieve range resolution and multi-band MIMO radars for enhancing the angular resolution. And finally, I will conclude my presentation. So this is our team. I have to give credit to students who have been behind the projects that I will be presenting today. So as of now, we have 6 current PhD students. One of our group PhDs graduated last year, is currently at Kyocera. And we have graduated 5 master's students and 6 undergraduate students who have joined academia and industry. And we hope to expand and enlarge our group in the coming year. Our research has been funded by several different agencies. First and foremost, National Science Foundation through multiple grant awards, and the most recent one, the Career Award, has been sponsoring our research. Army Research Lab, National Center for Manufacturing Sciences, and we have had some industrial support from companies like MFlex, SaberTech, and Global Foundries. And for measurements I'm going to show today, we are highly indebted to Keysight and Rodian Schwartz, who have been generously sharing equipment with us for the last couple of years. So our team mostly focuses on millimeter wave and terahertz frequencies. I guess for the audience of this presentation, I don't have to give textbook definitions of what that means, but to just recap the concept, millimeter wave in our terminology refers to any signal that has a wavelength going from 10 millimeter to 1 millimeter, corresponding to 30 to 300 gigahertz, and terahertz corresponds to wavelengths spanning 1 millimeter to 0.1 millimeter, which corresponds to 300 gigahertz to 3 terahertz. We have been working on various chipsets. Some of them are from my graduate school and postdoc time at Cornell in Michigan, and some of them are the recent chips that we did fabricate during the time I have been at UCI. So as you can read the description of these chips, since we have started our group at UCI, we have been heavily focusing on millimeter wave radar solutions. And as I'm going to go over 2 of the recent examples today, we have been investigating circuit level solutions for radar, such as this low noise 76 to 82 gigahertz VCO that was presented in RFIC 22, as well as comprehensive radar solutions, such as this work, which I'm going to present today, as well as some VCO that we recently published in JSSC, and also the other radar solution we did for MIMO FMCW radar, and an ongoing radar solution that we have done for monostatic FMCW radar with angle of arrival capability. So in addition to chip design, our group is also investigating antenna design. It's not only a complementary research, it's in fact well needed for any team who does wireless research. So ever since we started our group, we did work on antenna solutions for various applications. In one of the first prototypes that we presented in APS 2021, we presented a flexible aperture coupled stack patch antenna using polyimide material for the first time above 100 gigahertz. This was a collaboration with Professor Payam Haydari's group at UC Irvine, and we did present this work in antenna propagation symposium as well as the transactions in the following year. We have also been investigating liquid wave antennas for the last 2 years because they come with unique features in terms of beam steering, which in fact goes well with the concept we have for FMCW radar for frequency scanning and changing the beam direction when the frequency is changing. This is a ongoing research project. I will not have immediate results, or actually the recent results of this radar work based on these liquid wave antennas in my presentation today. But I will just want to show this and tell you that we are also heavily investing on antenna design as part of our research group. So for millimeter wave radar applications, there are various scenarios that they can come useful. So this photo that is from a paper we published in IEEE Communication magazine in 2020 is giving various scenarios that humans and machines can interact together, and you will have a sharing of information or alarming a user of any approaching vehicle or train or any moving object, as well as situations that you want to monitor manufacturing in human-robot interaction, or simply just do indoor monitoring for household applications or any indoor residential or commercial building. So the key here is radar solutions we want to implement should have sufficient range of coverage, and they should come with various measures of resolution at the highest possible level. So that's what we expect from these radar solutions. But it's not only radar that will be revolutionized when people investigate radar architecture. So as I guess a majority of audience here may already know, radar and imaging go very near each other in a sense that you can in fact use a radar chipset for imaging purposes if you only change the number of pixels that you're capturing. So the demo on the left side shows how you can use a radar for inverse synthetic aperture radar imaging, or ISAR imaging, which essentially shows that the major difference of the two is on the number of pixel data points that you're capturing. You can also use radar technologies for biomedical sensing, for example, breast cancer detection, hydration sensing, or any superficial features near the surface of the skin can be detected with the current state of millimeter wave radar. And last but not least, you can think of autonomous systems and robotics that can be highly taking advantage of advances in radar systems. What is the major push for CMOS radar is, however, two very highlighted applications. So one is autonomous vehicle. I guess this has been a very attractive topic for the last 5 or 6 years. A lot of companies are transitioning into electric vehicles, and the next thing they are doing is equipping those electric vehicles with autonomous functionality. Famous example of that is Waymo in San Francisco. If you ever travel, you will see those Waymo cars, which are self-driving. And the smart manufacturing is another line of research that can highly benefit from these CMOS version of millimeter wave radar. But when we say CMOS, immediately three major bullet items will be ignited in our mind. First thing is, in commercial and mass production, CMOS turns out to be low cost. It comes with a compact form factor, and most importantly, CMOS solutions are still among some of the most power efficient solutions. So if you want to have a solution for millimeter wave radar that can satisfy all the three criteria, one of the first candidates for technology that we will choose will be CMOS. Now, I have to make a fair comparison before convincing the audience or just trying to show the leverage of millimeter wave radars of why we are pursuing them. And it's fair to compare them against one of the main competitors, which are LiDAR technologies. So in fact, the example I brought for Waymo cars, they are equipped with both millimeter wave radars and LiDAR. So pretty much in many areas of performance, LiDARs and state-of-the-art radar technology, they come pretty close. So I would say in terms of range resolution, angular resolution, minimum detectable distance, and even distance or maximum range of coverage, they are pretty close. So millimeter wave radars had this caveat of the smaller range when they were early investigated, but as of now, they can go up to 200 meters in commercial products. So they are kind of near to where LiDAR can achieve. But the major limitations that come to LiDAR are in terms of the scalability and the possibility for making it compact and integrated with other elements of a perception system, as well as the portability and the phase of incidence acquisition. So I have to clarify that LiDAR systems can only detect time of flight. But what we may need sometimes for precise 3D imaging of a scene should be a phase of incidence information that millimeter wave radars with Doppler capability can provide that. Now, talking about radars, within the domain of millimeter wave radars, we also have to make another comparison. I have listed the three main candidates of millimeter wave radar technologies here: FMCW, which is the topic of this presentation, pulse radar, and Doppler radars. So FMCW radars, in a nutshell, provide sufficient level of range resolution, velocity resolution, and minimal detectable range. What is the limitation of a standalone FMCW radar is the possibility of angular resolution to become very fine and very narrow, but that is also something that can be achieved when you use FMCW radars in a MIMO fashion, multiple input, multiple output, or essentially multiple transmitters and multiple receivers. On the other side, Dopplers and pulse radars, they are actually very limited in the range angle mapping. Basically, you can hardly use them to obtain both range and angle information at the same time. And even for Doppler radars, because of the periodic nature of the phase, range resolution is non-definable. Basically, you can only detect vibrations or small motions with respect to wavelength using the Doppler radar. So this is why FMCW radars, as of now in 2025, are still among the most highly pursued candidates of radar technology at the millimeter wave frequency. So before moving forward to focus on FMCW radars, I want to do another recap slide here. I'm sure audience knows these, but I just want to refresh everyone's mind. We want to define the three major types of resolution for radars that we care most about. First one is range resolution, which is the capability of radar to detect objects in line of sight with minimum distinguishable distance. In FMCW radars, it is proportional to inverse of bandwidth. So the larger the bandwidth, the finer the range resolution becomes. Angular resolution refers to the smallest distinguishable angle of objects that can be resolved. We will revisit the formulas for both merits of resolution, but as of now, we want to mentioned that angular resolution is proportional to the array aperture size or antenna array aperture size, which is proportional to wavelength over the antenna spacing. And the last merit of resolution we want to refer to is the spatial resolution, which is basically using the collective performance of a radar in terms of both angular resolution and range resolution, which is for distinguishing objects in a 3D scene. So with these reminders and recaps of the content, we can actually move forward and discuss what functionality and what architectures are needed when it comes to our FMCW radar. So let's first visit the concepts of operation for FMCW signal. So you have a transmitted chirp that is continuously sweeping the frequency. You can have a sawtooth profile or you can have a triangular profile. And when this chirp hits an object, it will be reflected with a time delay, and the delay is going to be proportional to the distance of object. So as soon as you transition from time domain to frequency domain, you can detect the frequency of the IF signal, which is the cross-mixed version of the TX and RX signal. And the frequency of the IF signal is going to be proportional to the distance of the object. Now, for single object, the situation is very simple. But the major challenge shows up when you actually have two objects in the line of sight of a radar. So as you can imagine, when an FMCW radar shines two objects at distances D1 and D2, you will have two versions of reflected wave with different delays reaching back to you. So when you capture the reflected wave and you construct the IF spectrum based on a fast Fourier transform, you will notice that by increasing the bandwidth of the chirp, you will get a finer frequency resolution in your FFT. So for a same time window, for a same windowing time of your FFT, if you increase the bandwidth, you will obtain a finer frequency resolution. That means that you may be able to detect objects that are nearer to each other, which corresponds to nearer peaks in frequency domain. So that's why bandwidth matters for our FMCW radars when it comes to the range resolution. Now, doing a recap on previous architectures that people have been proposing when FMCW radars were being implemented on CMOS technologies, these two architectures shown here have been widely pursued. So one of them actually uses an external tunable signal to generate a chirp that is going to be multiplied by frequency multipliers brought up to the desired frequency of operation. And then through a antenna, the signal is transmitted. You have a directional coupler to provide some PX to RX isolation. And then you can get a version of the signal, version of the chirp to mix it with the mixer as the LO port of the mixer, and then get the reflected wave from the antenna on the receiver side and do the baseband processing on the IF chirp. So this thing is coming with an advantage of a simpler architecture, but it comes with limitations on frequency tuning and receiver sensitivity, as has been investigated by people before. Another possibility to make things more on the chip is to use a VCO level chirp generation. Basically, you use the frequency tuning of a voltage control oscillator to generate a chirp, and then you do the same signal routing similar to the other architecture. The issue here is that VCOs normally come with limited tuning if you want to maintain a high quality factor. The frequency tuning profile of VCOs are very nonlinear. And if you want to, in fact, enhance the bandwidth of a VCO to achieve a finer range resolution, you will have to sacrifice for the phase noise. And as we have shown before in some of our previous work, phase noise of FMCW radar may be very important for limits of operation near range resolution. So then comes a frequency trade-off, which is actually very critical because in the earliest development of FMCW radars, frequencies above 200 gigahertz were initially favorable because of higher unlicensed bandwidth and a larger absolute bandwidth that you can obtain. Obviously, you can get much larger bandwidth at the expense of degraded receiver sensitivity because of larger noise figure, degraded phase noise because of lower Q of the passive components, and most importantly, you will have to deal with an excessive propagation loss. If you want to alleviate these issues and operate at the lower frequency side, you may actually have to deal with a larger wavelength, which will limit the lateral resolution of your radar, which is a function of diffraction limit. And also you will have access to a smaller amount of bandwidth, because if you have, for example, 10% fractional bandwidth, 10% at 300 gigahertz corresponds to 30 gigahertz, at 30 gigahertz corresponds to 3 gigahertz. So we have some bandwidth issue when it comes to lower frequencies. But then looking at the propagation loss of these radar systems compared with communication or wireless links, we can in fact find that the propagation loss is a more severe issue in a radar system. If you are designing a communication link when a signal is transmitted from the transmitter side to receiver side, we all know from Friis equation that the path loss is proportional to d squared. For radar, you have a signal round trip. It has to hit the object and then it travels back. So you in fact have a d to power of 4 dependence. And this is actually something that heavily lowers your received power in radar systems compared to communication systems. And that means that for radar's operation, we do have to worry about the propagation loss if we want to operate at very high frequency. But then if our solution is to move to lower side of frequencies, let's say below 100 gigahertz, you all know better than me that the spectrum below 100 gigahertz is highly congested. We have so many license bands. We have very limited license bands for radar solutions. And if you want, if you want to design radars that are very high resolution in terms of range resolution, we don't really have resources for that kind of bandwidth at frequencies below 100 gigahertz. So then the question becomes, how can we achieve this level of performance at frequencies below 100 gigahertz? So that is in fact where our title proposal or idea comes into the game. So imagine I'm using frequencies below 100 gigahertz where the spectrum is congested and I have limited access to bandwidth per license band. So imagine I have 4 license bands for radar. They are separated with a non-homogeneous distance. For now, you can imagine one of them is going from F1 to F2, F3 to F4, 5 to 6, and 7 to 8. And they each come with their own time of frequency sweep, and each come with their own slope of the chirp. So as you can see, the time domain representation for the transmitted signal can look like a simple form like this. But then we have to find solutions that if you want to operate these radars collectively, we take advantage of their combined bandwidth. Is that something that is always guaranteed? We don't know yet. So there is this notion of frequency stitching, which is the idea of combining baseband signals corresponding to multiple different radars. And the idea has been proposed in remote sensing and radar societies quite a while ago, but implementation of this idea is actually very challenging for several reasons. So if you look at the transmitted waveforms that I introduced in the previous slide, and you find the corresponding received signal for them, then you will see that the IF terms will come with phase arguments that are proportional to the distance, and there are some negligible terms which we can simply dismiss. But then if you decide to stitch the signals corresponding to 2 separate bands, you have to make sure that the phase of the transition point is a deterministic phase. If this phase information is random, stitching the waveforms from 2 separate bands is useless. So imagine in a simple case, I design a radar with 2 subbands where the signals each has a duration of TR and I stitch them in time domain, and I want to make sure that I take advantage of the enhanced bandwidth of the two bands combined. So if you look at the phase of the first IF term at TR and the second IF term at 0, which is essentially meaning that you have the signal corresponding to the first band and then you immediately attach it to the second signal band, the delta phi between these two will become deterministic if you have a fixed frequency relationship between the two stop bands. So what does that mean? It means that in my previous slide, if I have two FMCW bands for which I can maintain the frequency relationship of the two bands, I can in fact stitch them together and I can enhance the radar range resolution to the limit of synthetic bandwidth, which is twice the bandwidth of each radar. So this is pretty cool when it comes for range resolution, and we're actually going to show a demo of this. But we have to emphasize that enforcing this phase and frequency relationship of two separated bands is a highly challenging task. Now, talking about range angular resolution, which is the other merit of resolution, there has been, a large body of work of pursuing MIMO solutions to enhance the angular resolution in FMCW radar. So how is this done for conventional radar? So the idea is you put a TX array and an RX array, you form a virtual array, and then based on the definitions we have for field of view and angular resolution, if you want to maintain the field of view to be sufficiently large, the only way to make the angular resolution finer is by increasing n, which is the number of elements you have on the TX and RX side. But this comes with a challenge that by increasing the n, you have to add the power consumption, and most critically, you have to have a precise synchronization and calibration between your TX elements and RX elements. So what can we do instead in the domain of multi-band millimeter wave radar is something simpler. So imagine I have two FMCW bands, one at a fundamental frequency F1 to F2, other one from 3F1 to 3F2. So if I form any MIMO array of these, you can see that for a fixed physical distance of L1 and L2 in X and Y dimension, I can have an electrical, for fixed physical distance of D1 and D2, I can have electrical length of L1 and L2. When I switch to the high frequency band, for the same physical distance, the electrical lengths are actually 3 times larger, which means that I am able to retrieve the field of view from the low frequency band, where I use the angular resolution, finer angular resolution of the higher frequency band. This is actually battling and challenging the trade-off that we have in single band radar for field of view versus angular resolution. So to recap, our proposal for this multi-band concept is under 2 umbrellas. One is designing phase lock FMCW signals if you want to use frequency stitching in range resolution enhancement. And the other one, which is a simpler frequency synthesis plan, is to use FMCW signal at 2 harmonically related bands, such that you can use the lower frequency band for field of view and higher frequency band for angular resolution. So let's go and take a look at these concepts into action and how we have implemented it. So for the first one, which is the coherent stepped-chirp radar, as I promised, we have 2 frequency bands that we are trying to maintain them at a well-defined phase and frequency relationship. If we can make this happen, you can stitch the signals in both frequency domain or time domain to enhance the range resolution to twice the value of each individual band. How can we do this? Obviously, PLL is the only option that comes to mind. Now, for PLL design, you all know better than me that if you want to use a single PLL that can handle 2 frequency bands, the PLL locking range and variation across the band is going to be very challenging to handle. And most importantly, designing a VCO that can operate under this condition is very, very stringent. So another solution may be a multi-PLL based structure. Imagine you have both frequency bands with their own designated PLL, PLL1 and PLL2, and you kind of find a relationship or a connection between the two PLL. This will simplify the design for the VCO, and it will make the performance variation less significant. But then, to make this two PLL architectures from an analog side of the story, we have limited number of possibilities. So one idea is designing type 2 analog PLL for each individual band, where we are using designated frequency dividers, charge pump, phase frequency detectors, and low pass filter for each of them. And we kind of find a way to share the reference signal between these two PLLs. But as you know, if we want to scale this idea of independent PLL for frequency bands, as you try to add more and more frequency bands to your radar to enhance the range resolution, then you come with a challenge on the power consumption. In fact, by adding more and more frequency dividers, and in particular, injection lock frequency dividers, which are our only chances at frequencies above 30 gigahertz, the power consumption is going to grow super linearly. So this is a very significant issue, and we have to find a better solution that we can scale our system, yet maintain the power consumption to be very low. So this is our proposal. We propose that you design a architecture that has one type 2 PLL as a reference. This can be the PLL for the first frequency band. And then for the other radar bands that you want to phase and frequency lock to this reference band, instead of designing designated type 2 PLLs with their own divider, you in fact mix the signal from the first PLL and the second VCO, and you mix them together inside a loop, inside a PLL loop, that will get locked to the frequency difference of these two frequency bands. So imagine if I want to have one frequency band at 50 gigahertz, another one at 60 gigahertz, instead of designing two PLLs at 50 and 60 gigahertz, I will design a 50 gigahertz PLL for the first band and a 10 gigahertz PLL for the second band. And that 10 gigahertz PLL is much simpler to design, much more power efficient. And then you can scale this idea by adding another mixing PLL. And this can go on to add more and more stop. On the receiver side, the situation is actually fairly similar. You have multiple frequency bands. Again, you will have the signal corresponding to each of them reach to their own LNA and mixer. And once you generate the IF signal, you can in fact combine them in FFT domain and achieve the stitching condition and enhance the range resolution significantly. So the final prototype that we designed for this chip is actually shown here. So as you can see, it's the full end-to-end radar solution with PLL, oscillators, power amplifiers, receiver side, and antennas all integrated together. So I will go over each block quickly, step by step, and then we're going to look at the measurement results. So for the PLL, as I said, we want to design an architecture that comes with a reference PLL on the left side and a mixing PLL that gets the signal from the first PLL, mixes it with the VCO of the second band, and then gets locked to the frequency difference of the two. As you can see by these simulation results, and I'm actually going to show the very exciting measurement results that we did for this chip, the portfolio of the chirp is highly linear, and the frequency error that we can achieve by this structure is very subtle. It's very minimal. So this is showing the potential of this architecture to allow us to achieve two phase frequency coherent bands with linear chirp profile and at the same time very power efficient operation. For the VCO design side, we have to be particular about what is needed. So as you can see, we have used a dual core cross-coupled oscillator to enhance the phase noise of the VCO, and we have done a mode suppression mechanism here by the addition of these transistors that you see on the top and bottom side, which will ensure that these VCOs that are in a very complex system only operate under the out of phase or differential mode, and in the in phase operation, the signal may not be basically generated. And the phase noise performance, as you can see here, is very competitive. It is in fact consistently below -100 dBc per hertz at 1 megahertz offset frequency at both frequency bands. So for the power amplifier design, we actually had to make sure that the power generated by each of the frequency bands is sufficient so that we can in fact reach our goal of having few meters of range of operation for the radar. So aside from the PAE and the matching conditions and the stability, the peak power of these power amplifiers that we have used in this chip, which are a cascade of neutralized differential pair power amplifiers, are both above 10 dBm. The signal going into each power amplifier is in fact passed previously through a frequency doubler, which gets the signal of the oscillators and generates a second harmonic. The reason we do this is because design of the VCOs at fundamental frequency and then passing them through the doubler is a more efficient approach compared to designing fundamental oscillators at twice frequency. On the receiver side, we have used LNAs, cascade inductively degenerated LNAs. 3 stages we have used to ensure that we have very high gain. The intermediate inductors that you see in these LNAs are for the purpose of interstage matching. We have to make sure we have sufficient matching on each LNA stage. And for the mixer side, we're using a passive mixer to achieve a better linearity. And we are also using a large buffer size to make sure that the noise figure of the mixer combined with the buffer is relatively low. So as you can see, our LNA single stages achieve close to 12 dB of gain with a noise figure which is around 10 dB. And the noise figure of the mixer and buffer combined is around 6 and 7 dB. So on the antenna side, actually, this was a very instructive effort for us. We, in fact, learned a lot from this integration of antennas on the board with the CMOS chip. So when we started to do this project, we decided to use wire bond for the packaging because obviously it was lower cost. And as you know, affording flip chip or more advanced packaging technologies is very costly. But then we learned that, in fact, for this particular case of this radar we're working on, wire bonds were sufficiently okay. Not perfect, but they were okay in terms of insertion loss. But when we combined the wire bond with the antennas on the board, we had to make sure that the matching conditions are perfect. And we have high isolation between the frequency bands. So the antenna bands we have used actually are each designed based on a linear fed patch series fed patch antenna array. And there is isolation between them based on the frequency spectrum of the antennas, as well as the wave confinements that we have between these GHz probes on GHz pads on each side. So this is the final prototype. As you can see, we have the CMOS chip, transmitter and receiver antennas on both sides. And for the purpose of more robust and less shaky antenna pattern performance, we have in fact shielded antennas on both sides with dummy antennas. So this is the chip fabricated in 22 nanometer FD-SOI CMOS technology. And we did multiple measurements for TX, transmitter characterization. So the frequency setup is shown here. For the sake of time, I'll just fast forward towards the measurement result. So we did the measurement of the power with both a spectrum analyzer using harmonic mixer, as well as power meter and power sensor. So for receiver characterization, we actually did single tone measurements, and we also did the combined radar operation measurements, both of which I'm going to show. So for calibration and measurement of power, we did the standard procedure that is done for fall-through power measurements. So you have to pass the Fraunhofer distance to make sure that you're dealing with planar waves. And after that, you will get closer to the Freeze formula prediction. And based on that, you can use the Freeze formula to estimate your EIRP. So as you can see, our EIRP is relatively high, around 8 dB, 9 dBm at both frequency bands. We were expecting higher numbers, as I said, wire bonds and the insertion loss associated with them, which was 2 to 2.5 dB, is highly guilty for this lower than expectation power. But then we did multiple measurements for characterization of the chirps at two separate frequencies. So as you can see, when the PLOs are not actually locked, you simply have two peaks at two separate frequencies, and there is no certain frequency relationship between them. As soon as you change the mode to the phase lock mode, you can see that by controlling the spacing between the two frequency bands, you can highly control the precise frequency of band 1 and band 2. Now, looking at this spectrum, some of you may already question that why are there so many spurs? Well, the spurs are happening because we have a mixture inside a PLO. But then the good news is these spurs do not matter for us at all, because as long as these spurs are further apart from the carrier than the IF bandwidth that we are interested in, the spurs will not impact the resolution and the certainty of the radar performance, as we're going to demonstrate in the IF domain shortly. This is in fact showing the phase lock phase noise spectrum at the two frequency bands, as well as the controlled chirp profile on a spectrum analyzer when we are dealing with large bandwidth or low bandwidth for the collective two frequency bands. So as you can see, you can operate this radar using two frequency bands to each being relatively narrow band, let's say 2.8 gigahertz combined, or you can actually use the total bandwidth of 10 gigahertz phase lock when you're using both bands at the full limit of their bandwidth. We actually did this measurement to the best of our knowledge for the first time, which is characterizing a chirp signal using the spectrum analyzer from Keysight. And we did demonstrate the chirp profile, the linearity of the chirp profile at both frequency bands under two different separate settings of bandwidth. In this measurement, because we did not have the chance to directly measure the high frequency chirp, we had to down convert it through a harmonic mixer. And because of the restrictions that we had on the frequencies of the LO port, we could not exceed the chirp bandwidth beyond 1 gigahertz. But as you can see, for both bands, within the locked region of operation, the chirps are extremely linear. And as we calculated the frequency error under both bandwidth settings, we have less than 2 megahertz frequency error for both stop bands in the low bandwidth and high bandwidth operation. We also did receiver measurements, as you can see, for various tones, and we were consistently getting a SNR higher than 20 dB in the IF spectrum. These are the results for the noise figure, P1 dB, and the gain of receiver. So the first, we did the noise figure measurement and P1 dB measurement by directly characterizing the receiver. And finally, this is a slide that we are super excited about, which does show the possibility of stitching the two frequency bands to enhance the range resolution. So as you can see, in the result that we got from one band, when we are dealing with objects nearby, it's very unlikely that we can distinguish them. But as soon as we stitch the signal of both frequency bands where we have the possibility for that, because we have a phase and frequency coherence, we can in fact find a finer range resolution. So we did range measurements up to 5 meters without any Teflon lens, without any external aid. And this was a record number for a radar with more than 14 gigahertz of bandwidth. So this is in fact showing the first radar in CMOS technology that can generate a bandwidth larger than 10 gigahertz and at the same time can achieve a range of coverage that is in meter scale range. So in summary, to compare this radar with previous art at CMOS technologies at both frequencies below and above 100 gigahertz, we in fact demonstrated the first millimeter wave radar below 100 gigahertz with more than 14 gigahertz free running bandwidth and 10 gigahertz phase lock bandwidth. Most importantly, this was the first prototype of a phase-locked step-chirp radar. The details of this paper is under a JSSD paper in early access. For the sake of time, I will just skip the comparison table and fast forward to the last part of my presentation. So as I promised, the other advantage of multi-band MIMO radars is for angular resolution enhancement. So we want to demo a radar that we recently tested, which is a MIMO setup. We have tested for 2 chips, where each chip comes with 2 separate frequency bands of FMCW that are harmonically related. Now, as I said, for MIMO operation, you need to be careful with LO synchronization. So this chip is also equipped with an LO phase shifter and phase synchronization among the chipsets. And we are using quasi-Yagi antennas for both frequency bands because our high frequency band requires to be a wideband antenna, and dipole antennas do perform better than patch antennas when it comes to bandwidth. So several trade-offs are hopefully going to be achieved here. Our high frequency band should achieve a higher bandwidth, which gives us a finer range resolution. Our lower frequency band gives us a longer range of coverage with a less bandwidth, which corresponds to less range resolution. So that's kind of similar to how our vision works. When we are focusing on a nearby object, we have a higher resolution. For objects in background, we have a lower resolution. So that's kind of similar to what we are trying to do here. At the same time, for the FOV versus angular resolution trade-off, we are in fact relying on the same concept that I proposed before. So we get the angular resolution from the third harmonic band and use the FOV, larger FOV of lower frequency band. So the phase shifter, we in fact designed 2 separate sets of phase shifters for the LO synchronization at both 25 GHz band and 75 GHz band. So as you can see, we need to make sure that the phase shifters are very low loss. For low frequency band, we are in fact generating the signal from the 4th harmonic of a signal at 6 GHz. So at 6 GHz, we are confident of using inverter-based cascode architecture for phase shifter. For the 25 GHz signal stand alone, when we want to tune the phase of the 75 GHz band, we do not employ a phase shifter directly at 75 GHz. In fact, we use this phase shifter, the separate phase shifter at 25 GHz band to offset any phase mismatch that we'll have at 75. And for that, we simply use a CLC structure, which comes with its quality factor limitations, and we do not want to use this at 75. So for the transmitter side, we have used frequency tripler for translating the signal at 25 GHz band up to 75. And for each frequency band, we have used a power amplifier to amplify the signal. So for a lower frequency band, we have higher power. We need less number of gain stages. We only have 2 power amplifier stages. For a high frequency band, we have 5 stages of neutralized differential pulse for the power amplification. And our tripler can actually suppress the fundamental by more than 18 dB. So we do not worry about the leakage of the fundamental. Receiver side, fairly similar to the other chip. This time we're using differential cascode single stage LNAs followed by passive mixer, as I said, for better linearity. And this is the final prototype of the chip. So we have 2 frequency bands, TX and RX. We have the phase synchronization and LO chain, and the combined operation of both frequency bands consumes 700 milliwatts of power. So the measurement results on the TX side does actually show that we are generating a very uniformly powered chirp at both frequency bands. So we are in fact generating more than 20 GHz FMCW, 16 GHz FMCW bandwidth, as you can see. And compared to simulation results, we are nearly achieving the expectations we had on power. Any mismatch, again, you see here is because, similar to the other chip, we are also using wire bond for the integration of off-chip antennas and the CMOS chips. We did a range resolution demo on the low frequency band, which is actually not the promise of this chip, but it is just to confirm the functionality that we can detect two objects that are separated by a few centimeters of distance. But the more important result is this slide, which does show that we have measured the power versus angle pattern at both low and high frequency bands. And for the lower frequency band, where we have the antennas at a 1.9 lambda spacing, we are able to achieve a larger field of view. For the higher frequency band, our field of view is smaller, but our angular resolution is finer. But then in the midst of this measurement, we found a very interesting result, which is the final remarks of my presentation, which is the fact that we learned if you have these two separate frequency bands and you decide to sweep the spacing of the antenna between the two bands, you may in fact be able to utilize the angle pattern of one band to shape the angular resolution profile and use the other band to only achieve the field of view. So what I mean by this is, imagine that if we change the antenna placement from the first version we did, which was 1.9 lambda fundamental spacing and 5.7 lambda third harmonic spacing, to another value like this one, we can actually achieve a very fine angular resolution, which is, almost 8 degrees. But most importantly, we can shape the side lobes and we can suppress the side lobes by tuning the two angle patterns such that the peaks of the third harmonic happen near the notches of the fundamental. So every time you're going to have a high powered side lobe because you have a spacing larger than lambda over 2, you can suppress this by the notch of the other band. And in your synthetic profile, you will actually have much suppressed side lobes that will allow you to achieve a fine angular resolution. So in conclusion, and to wrap up my presentation, I want to mention that these multi-band millimeter wave radars, for which we demoed, 2 chips, and we are actually investigating that idea further, have huge potential to revolutionize the way we think about resolution of our radar system. One of the reasons I'm excited to share this result with the Dreams community is because, as I mentioned, in the primary measurements of this chip, we had limitations in terms of packaging. And in fact, we could have in fact benefited from a higher power technologies like 3.5 devices for the power amplifier side to enhance the range of operation to commercial limits. So by this, I would like to thank you all for attending this presentation and listening to me, and I will be happy to answer any questions. Thank you very much.
Thank you very much for the great talk. Questions from the audience?
There were some comments in the chat. I don't know if those people wanted to follow up on them.
FMCW LiDAR is a common technology with all the, yes, of course. As I said, FMCW LiDARs have also been investigated. For CMOS, the main advantage comes to the co-integration with other technologies and, more chances we have on frequency synthesis. For example, the PLL designs and, multiple integrated elements that we can put on them. But yes, your comment is well taken.
Other questions? Maybe not a question, but a comment, which is that the California Dreams Hub and Moses 2.0 are working in collaboration with others. We're not ready to announce anything yet, but we are looking at an opportunity for GaN fabrication with some level of subsidy for interesting projects. So if you want to follow up on that interest you had on the left side, watch for that opportunity, and I hope you'll consider putting something in. We're also thinking and working a lot on heterogeneous integration and packaging technology. So our interests are aligned there.
Sure.
There's another question in the chat. Isabella, would you like to come off of mute or? otherwise-
Sure. Can everyone hear me okay?
Yep, sounds great.
Yeah.
Sure. So I'll just read from chat. So my question was, like I heard earlier in the presentation, like this kind of technology can be used to detect things like breast cancer. So I want to, if possible, could you speak to this research's other potential application in biomedical sciences? And like, would this include like radiology, imaging, or am I thinking kind of like very like far ahead?
Sure, great question. First disclaimer is I'm no bio expert, so my answer will be more on the engineering side of the problem. But to my understanding, one of the reasons we want to focus on superficial features like breast cancer or other disease that are not too deep inside the body is for the limitation we have on the penetration depth of our millimeter wave technology. So what we actually need is a highly accurate imaging modality that can detect the signal, and it can in fact acquire an image pretty fast. So right now, for anyone who wants to do any screening, CT scanners or MRI scanners are actually pretty fast. So the major limitation in extending CMOS solutions to bioimaging side of the problem is to design large arrays or integrated synthetic arrays such that you can in fact make an image acquired much faster. You cannot in fact go by pixel illumination of body that will take for hours to create an image. So the major limitation right now is the time of acquisition. But once you can do that, the level of resolution you can detect anything near the skin surface is going to be sub-millimeter scale potentially. And sub-millimeter scale, to my knowledge, for various disease is sufficient level of resolution and accuracy that you need to have a confident decision making. Obviously, for things that happen at a much finer level, like tissue level or cellular level, we cannot claim anything on this technology yet. But for a tumor detection or any abnormality detection that is having a feature close to millimeter scale in the earliest stages, that can in fact be detected. The time is the biggest challenge right now.
Thank you so much. That gives me a lot of insight. I appreciate your insight and your research, Professor. Thank you.
Thank you.
Thank you, Isabella. Do we have another question? If not, I will encourage everybody to go to the technical seminars for California Dreams site. The QR code is there now. All of you are on, must have found that at one time or another, but please follow us and watch for the next one. Thank you again very much, Hamid Reza, for the good talk today. It was great, and we had a very good turnout, especially going into what is a holiday weekend for some. We have a great lineup of speakers coming up. Next week, we have a combination talk between PDF Solutions and UCSB, Steve Zamek and Brian Thibault, which we're very glad to have as part of our hub. The week after that, the first week of May, Jonathan Hacker from Teledyne, Subu Iyer, who has recently returned from a stint in the government as the lead for the NAPMP program, back at his regular post at UCLA, and we're glad to have him talking. Chi-Wei Wang, also from UCLA, the week after that on May 16th. And then May 23rd is the Friday going into Memorial Day weekend. And so we'll take that week off. I think that's the first week we've had scheduled off since we started this seminar series, aside from a few cancellations. Last thing I'll say is you can find archive talks on our YouTube channel. Search for California Dreams on YouTube and you'll find it. And please like and subscribe those videos. I hope I sound like a real podcaster when I say that. Thank you again, Professor Agazi, and thanks to everybody in the audience today. Okay.
Yeah, thank you very much, everyone, for attending the talk. It was a great pleasure. Have a good rest of the day. Thank you.
Okay, thanks.